Okay, Liu Yang, let's go.
Okay, today let me show the paper reading about global climate disruption and regional climate shelters of the Toba super eruption. So I will give the sharing about the four parts. The first part is about the author. His name is Benjamin A. Black. He's an assistant professor of the Rutgers University, and his lab is Rutgers Volcano Lab. His research interest is about magma, magmatic volatiles, and planetary geology, and paleoclimate and Earth history. And he's a totally expert about the volcano. And the second part,
I could add a little bit to introduce Ben Black. I know him to a certain extent well. So Ben had got his PhD at MIT back, I don't know when, maybe 2014 or something like that. So in his PhD, he measured natural samples. So he's an actual chemist. So analyze the sample compositions, something related to the volcanic process. Then when he did a postdoc at UC Berkeley, he was working with Michael Manga, who was a geodynamics. So he ran different geodynamics models to see the impacts of large igneous provinces, for example, to the paleoclimate. So basically he ran a model during his PhD, during his postdoc. And then when he moved to Rogers, it looks like he's still combining different things, so let's still move forward. And on Wednesday, he's going to give a talk about the large igneous provinces. I think to a certain extent, this Toba one is just one of this, that's the most recent large eruptions, but he's also going to talk about the paleo ones. So, but for this one, including this paper, that it basically also combines more. It goes beyond the geodynamics in solid Earth, but also consider the atmosphere, ocean, as well as IC models. So it's very, it's open system. He is quite open-minded in observe a lot of new things in his research. So it's very interesting. So go ahead, Liang.
Okay. And before introduce the paper, or that I will give some background knowledge to you, because it's a paper about atmosphere that Mr. Jones just mentioned. And the first background is the Toba eruption. That is the key words about the title. And we will have the three questions about that. What is the Toba eruption and why it is so important to study, and how could it relate to climate? The Toba eruption is in the Sumatra Island in Indonesia, and this erupted 1.2 million years ago. But the latest eruption is in 74,000 years ago, and it also named Young Toba Tov. And the two characteristics of the Toba eruption is the superscale and the key time. The superscale is about the YTD is the largest volcanic eruption of the past 2 million years. And its eruption creates 5,300 cubic kilometers magma, and the eruption cloud and cloud can be the 30 to 40 kilometers is really high, and ash can spread across Africa and Asia. And the key time is about the eruption time is the early humans were supposed to expand more broadly beyond Africa. So it's a really key time about how people go to the Asian and some other lands from the Africa. But the consequence about climate is still debate now. So let's talk about the consequence in this paper. And the second background is about the CSM. It's the method about this paper. So we also have the 3 questions about that. The first is what is the CSEM and what is the role and how to use it. The CSM is the Community Earth System model, and they use the version 1.3. It's a 3D global climate model that couples atmosphere, ocean, and sea ice components. And they manually use the atmosphere model in this paper. And the model has 2 roles in this paper. The first is to simulate the physical and chemical impacts of the Toba eruption. Their version is the whole atmosphere community climate model. And the second role is to investigate the global climate response to the Toba and the regional climate response in the Southern and Eastern Africa. And the table is about their parameters of the model. They have 5 parameters. The first is round numbers, and the second is sulfur emissions, and the third is time of the year, and the fourth is emission attitude and the duration. The key parameter is the sulfur emission. It's very important in the discussion in later. And the time of the year is also very important. And the third background of this paper is the previous study. The first is about the Toba's impact in previous study. That is also controversial now. For the impact to human, there are 2 opinions. The first is the environmental disruption due to the Toba was modest, so it didn't hurt people very strongly. And the third is the severe volcanic winter will decimate early humans. And there are 2 evidence to support the first opinion. The first is there are 2 arcane ecology sites in Southern Africa demonstrates that early humans in these locations flourish through the eruption interval. And the second evidence is that the records of the charcoal and plant fossils from the Lake Malabar is also in Africa. Didn't show the large variations in the vegetation across the Toba interval. And the second is what is related to the climate change. There are 3 parameters about that. The first is sulfur aerosol. The sulfur emission from the Toba is a huge range. There are from 70 to 6,600 tech sulfur. It will influence the surface temperatures and ocean circulation, hydrology, and atmosphere circulation. That will lead the Earth's surface temperature cooling and the precipitation reduction. And the second parameter is the eruption time of the year, but the uncertainty of this parameter can be translated to the uncertainty in background climate state. And the third is the background climate state. It can influence the hemispheric bias in dispersion of aerosol cloud driven by the shift of the sulfur injection attitude, and the emission attitude is also impacted by it. Now is the third part of the process. The first question we get to know from this paper is how will the global climate change after Toba scale eruption? Now let's see the picture, and the upper part is about AOD and the bottom part is about a temperature anomaly. We could see there have the same shape, similar shape in this picture because we can see in the 2000 tech server, the peak is around 1 to 2 years after the eruption, and the AOD peak is around 1 to 2 years after eruption. It has the similarity. And also it's the same situation of the 200 tech server. The peak of the AOD is around in 1 year, and the peak of the temperature anomaly is also around 1 year. So the AOD is related to the cooling strongly. And this picture also shows the time of the year of the eruption has the difference about AOD. Now let's see the left picture. We could see the September eruption and the December eruption. They shows a high AOD around the 4 pictures because their color is more like orange than others. And we could see another thing is that it's really different between the northern and the southern Earth, because like the shape is more, it has a more left and is more right. So it's different between the 2 parts of the Earth. And let's see the right picture. Has shown the difference of the aerosol altitude of the injection. Is of the 35 to 50 kilometers in the 2000 tech, and is the 20 tech of the sulfur. In the same height, their color is similar, and in the same emission of the sulfur, but in different height, they also shows a very similarity. So it didn't impact the hemisphere transport of the aerosol cloud strongly. And see, this picture is about the global mean precipitation after the eruption. We could see the difference between the 2 tech emission. In the 2000 emission, we could see the peak is about 15%. And we could see the 20 tech server is almost just around the 0 line. So it didn't have the significant change, but the 2000 tech has the strong influence. So, but the result is consistent with the slowing of the hydrological cycle associated with the global cooling. That's the previous study in the orders. And the second questions we got to know in this paper is, does it have the same impact around the world? From this picture, we could see the answer is no, because the climate response in Southwestern, just like this picture, the Eastern Africa shows a really difference from other continents around the world. We could see the color means the temperature anomaly, and in the Africa is around the slight blue, but in the Europe and the North American, we could see is a deep blue color. It means they were cooling around 8 to 10 degrees. So there are really difference in the regionally. And from this picture, we could see this in the 20 tech server is in different height, and it shows some key information is about the confidence. There are some areas in the Africa shows the confidence under the 90%. The confidence is calculated by the Wilson rank sum test. It's a method to calculate whether it have the same characteristics. So it really shows some areas in Africa have the different characteristics from the other regions around the world. And in this picture is about the precipitation. It also shows the difference from some areas in Africa and other regions around the world. Just from the color, we could see the red color means the precipitation will decrease, and the red color means the precipitation will increase. So in some parts around of the Africa, we could see the red color, and also we could see the green color. But in the Europe and in the North Africa, it's almost red color. And in this picture is a picture about the likelihood of the situation, like 4-degree cooling and 40 degrees in precipitation. And just in the left 3 picture, we could see in the situation of 4-degree cooling, the North Africa and North America and Europe shows a likelihood over 90%. It's almost 100%. And in some parts about Africa and North Earth is almost near 0%. And let's see the right pictures is about the 40 degrees in precipitation. In some parts about the Europe and North America, it also shows the same characteristics, like it has the high likelihood. And in the parts of the Africa and South, in the South Earth, it also shows the same characters like the right picture. They has lower likelihood. And the third questions we got to know in this paper is, how does the turbo eruption impact human activity? They offer in this paper, the author an opinion is that the turbo may have strong effects on surface temperature, but not in the region where anatomically modern humans were thriving. Just also see in the picture, because at the time of the eruption, of the Toba eruption, the early people live in the Africa, and after the eruption, they have the tendency to go to some parts that is outside of the Africa. So at the interval of the eruption, the people mainly live in the Africa. And in these parts that is Africa, their precipitation and the temperature didn't strongly influence by the eruption. So that's the opinion. They think the surface temperature and the surface temperature cooling and the precipitation reduction didn't show in the region where early human living. And the conclusion is they identify significant regional and hemispheric difference in response to a global scale eruption. And understand it can let us understand the temporal changes in climate relevant to humaning and migration, and to inform the estimates of the climate effects of the large-scale sulfur release from the future explosive eruption. Yeah, that's all.
Okay, thank you, Liang. Thank you very much for let us go through this paper. Yeah, let's first see what the questions that we have. I think that as you read this paper, I think that for people doing research, that you should have some question in your mind. At least they should ask for clarification. So Lei, what do you think? So Liang, do you have any idea about it? About the aerosol optical depth? So the higher the ALD, that means what? So what is the unit here for ALD? Kilometer? Something? So Liang, is the ALD unit here kilometer or some parameter?
Because the AOD means the aerosol high altitude, because the aerosol will emission in the air and it has the altitude of it. So the AOD means it. And this picture
is how high. So that is how high that being thrown into the atmosphere by the eruption, right?
Yeah.
Then the higher it is, then it tend to reflect. It tend to. So for aerosol, that it try to reflect light away from the surface, right? So that it could cool the surface down.
Yes.
So the higher AOD it is, then the lower surface temperature it corresponds to. I think is that what this plot is trying to tell us, I suppose.
Yes.
Okay, so Ben, what is your idea about this paper?
So my question is, where is their recent data from? Like in this figure, there's June and December and March eruption data. Is a recent emission or something?
Recent emission? What?
Yeah, in this figure, it's June, December, and March. So is that what they are simulating their model?
Okay.
So as an aerosol, so late for aerosol, it results in. So the high, my understanding is that for higher the LDT is, then the more aerosol that flying in the atmosphere, so that the less light. So for the solar light, less of them will travel to the Earth's surface, and therefore the surface temperature is cooler. So the result is that the surface temperature is cooler. So that's what they are seeing, the plot.
This plot just to show the AOD, the relationship between AOD and the temperature cooling. It means the AOD can be a symbol of the temperature anomaly.
Mm-hmm. So, and they do have a mechanism to explain that. So that's good. So for Ben's questions that showing here, it shows two theta in terms of June, December, March, and September. So I think that's what they are doing for their simulation, that they're trying to simulation for the effects after 10 years of eruption. So basically they are, I don't know that whether they know the exact time for the eruption take place. I don't think they really know is January or something like that. But at least they could assume anytime it begins, then it let a model run to simulate what is going on for 1 year, so that they could see in different seasons what are the results. I think that's my interpretation for it. Maybe Riyang could correct me if I'm wrong.
Yeah, this picture, this pros just to show in the different seasons, the AOD can show different influence about the Earth, because this circulation in the stratosphere can influence the season, and in different season, the climate is different in nature, right? So in different climate season states, it will have the different influence by the AOD. That's the same as the opinion Mr. Zhang mentioned just now.
Okay, so Chuntao, what is your question and idea? This paper?
Why there
So
is no
11
difference
page.
between the model result? I think it seems. Why there are no impacts on sounds option?
So Chuntao says that he's wondering why there's no difference between the model results. Because if they claim that actually the paper, they claim that the northern and southern hemisphere do have a difference, the northern hemisphere temperature drops down. The southern hemisphere in particular, in Africa, in the middle Africa and West South Africa, the temperatures actually increase a little bit, I think.
Do you mean this picture have the difference between the 200 and the 2000 tag? Because this is around the yellow color, and this around the yellow color, and this only the blue color. Yes, I also feel confused before, but this is about the different altitude of the sulfur is around 18 to 25 kilometers. And they said in his paper, this altitude in 2000 tag didn't influence so much, but the big difference is between the 2000 tag and the 20 tag.
So my interpretation for
They
go
means
ahead, go ahead.
They means the altitude in the lower tag sulfur didn't influence so much, but in the higher emission, like 2000 of sulfur, the altitude will influence strongly. So that's why they
so
show
here
the
when they
picture.
say the 35, so when they saw the 35 to 40 kilometers, they mean 35 to 40 kilometers away from the Earth's surface. So how does the AOD affects that, right? So okay, I'm a little bit confused. So if it's 35 to 40 kilometers, the AOD basically is the aerosol optical depth. No, so what is, no, I'm confused by AOD now. So is AOD by how thick the aerosol are to prevent the light from getting in?
I don't think so. I think this picture just wanted to show the 2000, the difference between the 2000 and the 200, and in the lower altitude and in the lower emission, the AOD didn't show too much. So it means the AOD didn't influence the temperature so much. And they also show in like this situation, 200 tag of sulfur and 18 to 25 kilometers, the AOD didn't make the Earth temperature cooling too much. They more focus on the two plots, the first plot and the second plot.
Yeah. Chen Hao lived there. Yeah. So they, of course, the higher the sulfur dioxide erupts, of course it will goes fully into the global circulation. At least that's what I think. Yeah, for the stratosphere, it circulates much better than the lower atmosphere.
I'm good.
Kind of their model predict the condition during the eruption. So what do you mean during the eruption, Arca? Do you mean that on the day of eruption? Because actually they erupt multiple times.
Can this
Uh,
the condition?
Actually, I meant that the conditions, like it has erupted multiple times. I get it, but it seems that there is a time gap between, like, they have taken for the last 20 years. So like, are they, like, they have linked the human migration factor to it, but like, from when are they starting it? Like, that is the doubt. Like, from when have they started the model?
Yeah, so Liu Yang, did they specifically say their model is trying to start from which year? I don't think so, though.
They have know which year the Toba eruption is 17,004.
74,000 years.
Yeah.
But that's the most recent one.
Yeah.
So it erupted many times. But in this model that they are showing, they assume it started from 74,000 years, or they don't make any assumption. They just say it could be any year during one of the eruption, maybe
No.
1.2 million years. Only the last one. Okay.
Yeah, only the last one. They just use this time.
Okay, 74,000 years.
Yeah.
And then they look at the archaeological records.
Yeah.
I say
They can.
the archaeological records, people claim that without human activities there.
They have the 5 parameters to simulate their condition. So what kinds of the condition you mean?
Yeah, so that's another thing that is relevant to. Yeah, Liu Yang, go ahead.
And what is the time gap? Where is the time gap? I didn't say the time gap.
Time gap.
Yeah, you means the gap between the different months?
No, I just meant that, like, they have made a continuous model, right? Like, it's not a discrete model, but then how are they linking the human migration? Like I didn't follow the archaeological parameters that said, so I got it. Like, my question is clear. It's fine.
Oh, okay.
Okay, that's the archaeological records. Yeah, they do consider seasonal changes because for this type of model, actually, I'm going to send this paper into our big data center here in our School of Earth Sciences here. We will do have other experts who are experts, other professors who are experts in the climate model as well as atmosphere chemistry model. So I think they are way more familiar with the model about it. I think it's a widely used one This is called the CESM, right?
Yeah.
I think it's a widely used model in the community. So they would know way more details. I don't think simulating the seasonal variation is a big problem. But what I have little doubt is that how well is CESM could apply to 74,000 years ago or even earlier, because it could be quite different than what we are now. For example, sea level should be different 74,000 years ago. If, for example, if you look at the Milankovitch cycle, which has, like, say, in my recollections, like 40,000 years, let's say 10,000, 100,000 years, and 400,000 years. Actually, it's approaching for the Milankovitch cycle. So it has occurred in the last glacial age, approaching the last glaciation. Of course, it has occurred. Now the human sapiens, excuse me, the human sapiens evolved after the last glaciation, but I don't think that the climate was exactly the same as what we are now. It should be different. And I'm curious that what is difference that what's that difference could impact for that. Actually, another question that I was
maybe I got stuck or my microphone didn't work. I can't hear your question, Mr. Zhang.
okay. Can you hear me now?
Yeah.
Change another.
Yeah.
Okay. So actually, I have another question. I think it's quite insightful for what they are doing now. For when we think about the paleo temperature, for example, the Toba eruption absolutely it affects the global average temperature a little bit, but they have the different effects on the northern and the southern hemisphere. So northern becomes much cooler. Some places for 8 degrees or 10 degrees cooler, but in the south is neutral, and even some places it increase a little bit. So my question is that, okay, if these similar things occurred throughout the geologic history, it must have occurred. We had large igneous provinces before. So if similar things occur, then suppose in the northern part, there are some other geological records that people nowadays use to approximate the temperature. So basically, the global temperature has a larger variation in different places, because my estimate for this Toba eruption is that it might affect the global average temperature a little bit. I don't know, maybe 2 degrees C, the entire globe temperature, but it really has different effects on different parts. So if we only use a certain geological record and say, okay, hey, this trying to represent the global average temperature, then of course it's not accurate. Then we need to know where that's the sample coming from, what the environment does it corresponds to. Because at least according to this model, at a similar time, not the absolute temperature difference, but in one location, the temperature variation could be up to 10 degrees C, according to this model, right? Some places cools 10 degrees, some place doesn't. And the global average temperature just change a little bit. So for me, that makes our geological records more troublesome, because they are going to have even larger uncertainty than what we might think, because that mainly depends on how biased the samples are really preserved.
They have offered imagination that is all of the scares like the Toba eruption can have the same roles, like just the Africa can be a shelter. But they also say the effect of the volcano eruption is really complex, so it needs more research in the future, and especially to find the records like the paleoclimate records to prove their imagination.
Yeah, but my concern is that probably it's very hard for people to find a paleoclimate record that first with a very high time resolution. I think for this case, maybe it's okay. Is that they are going to find a paleoclimate record that still exists in one location but doesn't move. Because when we talk about geological history, the geological records in the geological history, those samples move because of the plate tectonics. At least for this one, you don't have to worry too much about it. Okay.
And I just see questions from our card. So who is that? How they link the human migration? Yeah, I just mentioned that's because the time of the Toba eruption is a really key interval that human would come to some other regions outside of Africa. So they think the time is really important, and they want to know if the Toba eruption have impact the region the people live at that time, is the Africa region. And they know the Africa didn't influence strongly by the Toba eruption, so they imagine the Toba will have an alternative impact in different regions, especially in the people live, in the region people live, they will have the modest influence. This their imagination.
Okay. Okay, I think it's pretty good, but I do acknowledge that I don't know CMSM very well. I'm going to throw this paper into our other professors. I will ask for their comments, and hopefully that they can come to our seminar too, and if they're interested in. And I think this is quite a good study for the collaboration between the atmosphere science as well as geological science. I think it's a pretty good question for that. Okay, thank you very much, Liu, for leading the discussion, and I really appreciate it. And thanks everyone for joining. So is there anything interesting this week? Arka, is there anything you would like to share?
No, actually, this week, like just a week before this was when our festivals ended. Like, so we had fun during that week. However, this week actually, my situation at my home is not very good because of my grandmother getting ill. But again, coming from 15th, we are going back to the campus. So the campuses are reopening. Almost all the campuses are reopening in India. So that is, I think, that is interesting going on over here.
Okay, that sounds good. You're good about the campus. I think that's pretty good. Okay, I think that's all about it. Okay, let's see the speaker on Wednesday morning. This time is slightly different because we're going to present on Tuesday his evening time, so it will be Wednesday morning for us. So yeah, let's see what they're going to speak about. But I think he will speak a lot about large igneous provinces because they have several publications on that topic in the paleo ones. But I do think he's going to talk about this paper too. Okay, great. Have a good evening, everyone. Bye-bye.